Welcome. Thanks for joining me on this session, um, where we'll be talking about Reactor and Reactor's execution model. I hope you had a nice lunch and that you're not too tired for this talk, which can get a bit technical. My name is Simon. I work on the Reactor team, on Project Reactor Core for Pivotal. And so I'll be talking about the inner workings of my project, our project today. But first, who here is not really familiar with Reactor or reactive streams, like publisher, subscriber? Okay, quite a few people. I don't have a slide, an introductory slide for that, unfortunately. But think of it this way. With Reactor, you program asynchronously by describing your data processing as a flow of several operators that you compose together. And this gives you a rich API to perform asynchronous computations in your programs. And it's based on something called reactive streams, the reactive stream specification, which defines a few classes, pretty simple interfaces actually, and also most importantly defines how these classes interact. And this gives us, like the implementers of reactive streams, the ability to interoperate together. So there's, for instance, RxJava2 and Reactor can exchange data because they have kind of a protocol in the reactive stream specification on how to interact with each other. And so you get a publisher which produces data and a subscriber who listens to it. And there's actually a bit of flow control in there baked in as well. That's called back pressure. And what basically happens is the subscriber, when it subscribes to its source publisher, it gets an object, a subscription, and this object can act as like a volume control. The subscriber can say to its source, I'm ready to consume that much data and not more. And the publisher must then follow that request and send, as it becomes available, it will send the requested data, and it won't send more elements than requested. So yeah, that's the basics of it. Should have probably put a single slide to show that in a diagram. But hey, I wanted this talk to be a bit more advanced technically, so what will we learn? We'll learn about Reactor, of course, but we'll learn about Reactor execution models and a few points about it. So for starters, you'll learn that nothing happens until you subscribe. And you'll learn the difference between what we call assembly time versus execution time, or data flow time. You will learn to differentiate between cold and hot fluxes. So what's the difference between a cold publisher and a hot publisher? You will learn that Reactor is said to be concurrent agnostic. You learn about the scheduler abstraction, and two very important operators for the execution model, which are publish on and subscribe on. And we'll also discuss something work stealing, and finally operator fusion. So that's our topics for today. All right, so first, nothing happens until you subscribe. What is this assembly time that I was talking about just now? So this is kind of a general statement that we make throughout the reference documentation, for instance. And what we mean by that is when you use the library, when you create a Flux, an instance of Flux, and then you call the one of the many operators on it, and you start describing a chain where you map. It's a bit like Java 8 streams. You map, you filter, you combine flux, you arrange them, you recover from errors, that sort of stuff. And as long as you're calling these operators, you're actually not starting any processing. You're just in assembly time, and you're just describing your intent. So you're not triggering any data generation, you're just describing the intent, what the pipeline, the processing pipeline will do. So it looks a bit like this. So you might have a myTest class, and you have an init static method in which you define an attribute of type flux, myFlux, to be just the value foo, and then you want to map that string that comes from the source into a length. So you call string.length, or in this case the method reference. And by doing that, you have just described an asynchronous pipeline where whenever it's ready, it will emit the string foo and immediately asynchronously transform it into the length. So this is a static example, just is not very useful in production code except when you want to generate constant events like that. But it gives you an idea of what I was talking about. So as long as you just call this chain in these operators, you are basically just describing a process and not triggering it. Whereas there's execution time on the other end, or rather I should say subscription time. So the final act that you can make on a flux is subscribe to it. And you subscribe, you pass a few lambdas where you say, what should I do with the final form of my data? So say in the previous instance it's an integer. What should I do when I receive an integer? Maybe you want to display it on the screen or print it to the console. How should you react if there is an error as well? And do you want to react on the completion signal, like saying this sequence is over, there won't be any more data? The most basic form, though, is just you subscribe and you don't do anything in particular with the data. But pro tip, you should at least define a handler for the values and a handler for the errors. But hey, there's this method called subscribe. And this basically tells the flux that somebody is listening, somebody is interested in the data. And that's where things start flowing through the pipeline. So let's take an example. Make an HTTP request, for instance. You have maybe the Web Flux web client as a reactive client, and you have an URL, and you want to trigger an HTTP request, retrieve some data from an API, and you are only interested in, like, the API will give you a flux, a sequence of several elements, and you are only interested in the last three, or the first three elements. So you could chain, after your HTTP call, you could chain an operator like take 3 to say, okay, drop the rest, I'm not interested in that. And so far, the HTTP request has not been made. And that when you subscribe, when you call subscribe at the end on that flux that you just constructed, then the HTTP request is made. So whenever you subscribe, it sends a signal back to the source, and the source starts emitting data, and then it flows through each step of the pipeline, right? So you might also wonder, what would you see in that case in a stack trace if there is an error in such a pipeline? Well, you would see something like that. So it's a big stack trace, but let's show the interesting part. Sorry, copyright issues. You see that you get an onNext you drill down to something called a request, and there you see that you start to see subscribe, flux.subscribe. And at the bottom of the stack trace, see mycode.test, mytest.java. So the stack trace is not really as relevant as it was with imperative code, because there's this difference between where you assemble your pipeline and where you actually execute it. And this could be, yeah, my test is the worst part, actually, because this points you to a part of your code where you called subscribe. And this could be anywhere in your app. You could have set up the pipeline way in another completely different service and do the subscribe right at the end, somewhere else in a controller or whatever. And this will give you less information, less relevant information, because most of the time you're actually interested in where you instantiated the flux, not where you started it. So a tip for that, there's an operator called checkpoint. It will attach an additional part of the stack trace to the errors. It has a cost, but it helps when you debug to see where things are coming from, where the Flux instances are coming from, and not where they are subscribed and executed. Okay, so that's assembly time on one side, describing your Flux operation, the pipeline, as I was saying, and execution time or subscription time, or when does the data start flowing. This is a good time to introduce the notion of hot and cold publisher. Basically, so far I was talking about a cold publisher. And what is a cold publisher? It's a publisher, like here I represent it as a loudspeaker. So it will produce some music, and the subscriber will be here's listening. A cold publisher is one that doesn't trigger the generation of the data if no one is listening, basically. And it will generate the data anew for each new subscriber. So in the case of the HTTP request, for instance, every time there is a new subscriber to this publisher, it will generate a new make a new HTTP request on the network. Here, if there is a new subscriber that comes in, the publisher generates some music and sends it to the subscriber. If a second subscriber comes in, the publisher generates the same music but a new instance, the same data but a new instance, and send it to the subscriber. And same for a third subscriber. So yeah, this is basically what I was telling earlier. Nothing happens until you subscribe, and each time you subscribe, everything happens back from the start, basically. Which is always true until it's false. Enters the hot publisher. So the hot publisher is another category of publisher, which simply it doesn't care about whether or not there is someone listening. So here it will generate some music as soon as you start it somehow. So it might be that the first subscriber starts it, but otherwise it doesn't really matter. And it will send the data immediately. And if nobody's listening, well, it's lost. If somebody comes and listen a bit late, it will only see the events that have been emitted after it's subscribed. So you can subscribe, like say the first subscriber comes in right at the beginning, it sees all of the sequence, all of the data. But another subscriber comes 2 seconds later, it will not see any of the data that has been emitted between t0 and t plus 2 seconds. So yeah, that's basically the two big categories of publishers there is. And most of them are cold, but yeah, you can come across some hot publishers as well. So it's important to keep in mind. So another thing, Reactor is said to be concurrent agnostic, and in terms of execution model, I think it's it's important to a point to make. Basically, Reactor doesn't force an execution model on you, actually. So it's more like it provides tools for you to choose where to execute your different steps in the pipeline, and we'll come to that a bit later. With one exception, time-based operators, they have to have a default. They have to run in kind of a default. Let's not say thread pool, but that's more or less the idea. Basically, they have to execute separate of the main thread. So if you start using interval or delays or stuff like that, these operators actually shift from the main thread to a thread called parallel by default. But you can change that as well. So you can decide to use your own thread pool. You can decide to use your own model on top of that. So in the API, look for methods that have an override which takes something called a scheduler. I'll talk about that in the next slide. And these operators, they have a default scheduler generally. So these operators tend to change threads in the middle of the sequence. So keep that in mind. But yeah, apart from that, you have the choice, you have the power, you have the tools to define, like fine-tune your asynchronous processing in terms of threads and execution context. And you do that using schedulers, and you do that using two other operators. Schedulers is an abstraction, kind of sits on top of executor service, if you will, but it could be backed by something entirely different. It allows to submit a task, like schedule a task immediately or after a delay or at a fixed rate. And it also has a time dimension in terms of measuring time, a clock, if you will. And we offer a few default schedulers. So there's a schedulers, plural, class. And on it, you have factory methods to construct new schedulers. So you have the elastic scheduler, which is backed by a thread pool that will grow on demand with a time to live. You have a parallel default scheduler, which is a thread pool the size of your same number of threads as you have CPUs. So it's bounded. You have single scheduler. You have a few different options. And where do you use this scheduler? You use it with an operator called publish_on. And that's the tool that lets you very easily switch from one thread to another right in the middle of your sequence. So say you have data that comes from a database. So the driver uses its own, maybe its own thread pool on the side. But it comes as a flux of JSON objects. And you want to, say you want to do some heavy processing. So usually you never want to block a source thread. So you'd want to jump to another thread pool that you have tuned for your app, and you would use publish_on to do that. So in the middle of your chain of operators, you put a publish_on operator, and you say, okay, from now on, the data that comes in, I will publish it, I will emit it on a different thread. So it works a bit like that. So say you have this sequence, flux.operator1.operator2.publish_on, .operator3, .operator4, .subscribe. So you trigger actually the sequence of events. And here we have the threads for each on which each of these operators will execute. So can you guess how it will look like? Would look like that. So the thread, the starter thread, is the blue one, and is the thread where you called subscribe. So if you call subscribe from your application.main method, it would be the main thread, for instance. And from where you subscribe and all the operators at the beginning of the chain, they execute in the blue thread. So they keep in the same initial thread. And then comes publish on. And publish on will change that and start emitting data that it receives on a second thread, the orange one. And from there on, operator 3 and operator 4, they will work on that second thread. So basically, thread calling subscribe is where the data starts flowing. And publish on jumps from one thread to another. And after publish on, data now flows in thread 2 for the rest of the sequence until it comes across another publish on operator, basically. Okay. There's another one, subscribe on, which is a bit different. So it's a bit harder to understand at first, but introducing publish on first makes sense in that case, because subscribe on, you could use it at the same place in your chain of operators, but it would have a different effect. Let me show you. So now it looks like this. It's all orange threads. So what happens? Basically, subscribe on, instead of being acting in the middle of the chain, acting on the downstream of it, basically the operator that follows it in the chain, it kind of directly touches subscribe. Like it tells subscribe where to execute, basically. So instead of, like before, instead of triggering subscribe in the main thread, the work of subscribe will now be triggered in the subscribe on thread, like the orange thread. And subscribe, as I was telling earlier, it influences where data starts flowing. So here you go. Operator 1 executes on the orange thread, and as a natural result, the rest of the chain executes there as well. So it kinds of publish on, if you see it in your code, in an intermediate position, it will only influence what's below it in terms of chain of operator calls. Whereas subscribe on, wherever you put it, it directly influences the start of the chain. And what if you combine the two? So yeah, subscribe on changes where sequence subscription happens, which is where data flows initially. Altogether, what happens if you combine the two? It looks like that. So let's say you have a subscribe on, you have a first operator, operator 1, you have a subscribe on, operator 2, publish on, operator 3, or rather 4, subscribe in the main thread, and you pass in a lambda that says what to do with the end result of that processing pipeline. So in this case, it receives a v, whatever, a string, and it does something with the string. But initially could have been an URL or a JSON object and went through a few transformations and ends up as a string at the end of the pipeline. And that's what subscribe, the lambdas that you pass to subscribe, that's what they see. So, and here we have like the starter thread, the one where you called subscribe, and here we have the thread in which the lambda executes. And it looks like this. So, what do we have here? The initial thread is the main thread, but subscribe very rapidly, it's overridden by subscribe on. So basically, you subscribe in the main thread, but since you have put a subscribe on, it doesn't matter. It will actually, operator 1 will actually execute in the orange one. And for that operator, subscribe on, and operator 2, it's still in the orange thread. And then comes a publish on, so it switches to the green thread. Operator 4 in the green thread as well. and it goes all the way to the end of the sequence. So as you see here, the lambda itself, the callback, the value call handler, sorry. I shouldn't say callback, it's a big no-no. So this one also executes in the green thread. All right. So you see subscribe on acts on the left and on the right, whereas publish on acts only on the right. Is that clear for everyone? Yeah? Okay, so that gives you a good first overview of what it looks like what happens at runtime and how you can influence that using publish on and subscribe on, which are the two basic tools for that job. So as you can see, using the power of composition as well, you can describe pretty complex pipelines and fine-tune how things execute. And also you can describe pipeline and decide later maybe where to execute it or when to execute it. So you could start assembling pipelines, and with logical branching you could add more steps or remove some steps and decide later where to execute all these steps. And you could change that after the fact, after you have built the pipeline, as long as you have not subscribed yet to it. You can change that by maybe attaching, if you receive a flux of T, you can always call subscribe on it, and it will influence the whole sequence, or you can chain a publish on it, and it will change where you consume the data at the end. Yeah. So that's the kind of the introduction to these elements. I have two other topics that go a bit deeper into how things work also in the background. And the first is what we call work stealing. So if I go back to what I said earlier, where do most operators run? Well, they run basically in the same thread from which they received an event. So in reactive streams, you have three events. You have on next, on complete, and on error. On next, you can get 0 to n. It could be an infinite sequence. So on next, it's the signal the subscriber receives when it gets notified of a new element being available. So remember the back pressure aspect. If the subscriber asks for 2 elements, it will receive at most 2. And the publisher might send these 2 elements with a 1-second delay, for instance. It's not a pool model. It's not like right where you ask for 2 elements, you will receive them and it will block until you receive them. No, it's just a signal that you send to the source. And whenever the source is ready, has enough data, it will produce it to you, the subscriber. So these on next events is determine where, in which thread they will run by just being called from the previous operator, except like until you come across a publish on. So operators will execute in the same thread until it changes due to a publish on or a subscribe on. Again, that's not entirely true for time-based operations. But then what is work stealing? You have some cases where one operator could combine data from two sources, and it might be that they kind of come from 2 separate threads. So there's something in the spec that that says on a single operator, the onNext method, it cannot be called in parallel with either onNext, onComplete, or on error. Uh, but in certain cases, when you combine data from two sequences, you can get a signal from two separate threads. And these kind of operators, they work with a queue internally, a shared queue, and use a concurrent programming pattern called a drain loop. And that's where work stealing comes in. So say you have the first thread to receive a signal is the orange one. It receives an on next. It will offer that value to the shared queue. And immediately it will start working because there's no competition. From its point of view, it's the only one working on data so far. And then comes in a second thread, right where the first one, there's a race condition or a race with the orange one. When the orange one is still doing some work, the blue one comes in, and it offers data to the shared queue. But then it will detect that somebody is already working. There is an atomic counter, a guard that will check if another thread is already doing some work. And since that's the case, the blue thread will immediately exit, and the orange thread will actually steal its workload. So basically, the data comes in the blue thread, and instead of processing it, it just puts it in the queue and exits. And the orange thread sees that there is still data in its queue, sees that it still has the control. So in a loop, it will steal that work and do another pass on the content of that shared queue. Yeah, and then exit. So it's a very recurring pattern in the implementation of Reactor core operators. But that's not something that you should really be concerned about, because this is done so that the operators are consistent with the specification and work well without locking, because there's no lock involved in here, despite what you could think. It's just an atomic integer, a compare and swap. The first thread that starts working, it expects the atomic integer to be 0. And if it's 0, it enters the loop, in which it takes an element from the queue, process it, send it to downstream. Whereas the other one, like the other possibilities that the threads arrive at this atomic integer, tries to swap it from 0 to 1, but it turns out it's already at 1 because the other thread is there already. So in that case, it's the blue thread. It would see it's already at 1, just put the element it received in the queue and exit, knowing that the orange thread would do a second pass and discover this work and steal this work. So yeah, it's really an internal concern. And the benefit of that is that there's no blocking involved, and also there's no thread switch involved. Like, it keeps the thread switches to a minimum. So sure, the data comes in from two threads, but only one of the two threads will win and do the work, the heavy lifting. So it could go on and on, like it could process the whole set of source data this way, whereas short-lived threads on the side will only do the offering to the queue. Is that clear? So yeah, that's work stealing. And yeah, finally, another last interesting aspect of how things run in Reactor is operator fusion, which is more of an optimization, but it's also it could also be interesting to keep in mind where you develop with the library. So what do I mean by fusion? Remember that you declare a pipeline, a processing pipeline, when you chain in a fluent manner, you chain calls to operators. And sometimes you might use the same operator a bunch of times in a row. Like you do a filter on that condition and filter on this condition and filter on that condition. So there's a first optimization called microfusion, which will help if you do that sort of thing. So for instance, you have a then operator. So basically it's you start with a sequence, and once it completes, then you start another sequence. Once it completes, you start a third sequence, and so on and so forth. So here you in your code you would call then, and it would instantiate internally three instances of the then operator. And with microfusion, we detect that sort of use case, and we'll actually combine that into a single instance of the operator. So you shave a little bit of the cost of doing that repetitive task by grouping that sort of task together. If you use Java 8 streams and IntelliJ, there's something a bit similar to that. IntelliJ will have a warning or an intention to tell you, oh, you in Java 8 streams you used map or filter 10 times in a row. You could actually just use map or filter once and just combine the lambdas or combine the predicates. And it's a bit similar, except it's done for you at runtime. Or rather at assembly time, because we detect that when you instantiate the operators, the flux. So that's macrofusion, so from a coarse perspective. And there's another form of fusion, a bit more advanced, called microfusion. And here it's a little bit different. It's not about combining instances of the same operator, but rather detecting some cases where you have a few compatible operators, like 2 maps in a row followed by a filter. And in the normal case, each of these operators would have a queue dedicated to it. So this is bounded queues that are used to honor back pressure. So if there is a little buffer of data that comes in more quickly than the subscriber actually requests, we buffer it, but in a bounded manner in internal queues, and then we serve it as more request comes in. But the problem with that is we instantiate 3 queues, and with microfusion we detect that that sequence of operators is kind of compatible with microfusion. There is a negotiation involved, so each operator will negotiate with its upstream operator and say, okay, are you able to use asynchronous fusion or synchronous fusion or none of the above? And they will negotiate which implementation to actually use. And it boils down to having a single queue traverse the whole subsequence of operators. So here again, we avoid the cost of instantiating a few queues and all that entails in terms of polling and so on and so forth. And we do something that traverses the whole sequence. And it could be bounded inside your chain of operators. If there is one that is not compatible, then it will only act on a part of your chain. But again, that's something, an optimization. So you don't really see it when you code against Reactor. but it's important to keep in mind that's how things can work in the background. Yeah, I wanted to add something on Fusion, and I have forgotten now. Good job. Yeah, so that's pretty much it for me. This is the end of the talk with a bit of leeway for questions and answers. So I'll be happy to take questions if you have any. I hope it was interesting, and I hope those of you who weren't familiar with the Reactor API are not too lost. Sorry. Do you guys have any question? Yep. Oh, looks like the microphone is not on. Yeah.
Hi, thanks for your talk and your introduction to the Reactor framework. Regarding the Spring Web Flux integration and also together with Spring MVC, Jürgen spoke in the talk before your talk about possible migration paths from MVC to Web Flux and so on.
Yep.
Do you know if it's possible if I have a Spring application which is using Spring MVC with Tomcat or Jetty or Undertow underneath to switch for, let's say, new endpoints to Web Flux with Reactor, and then using an adapter for Tomcat or Jetty to use Reactor in these applications as well?
So the question is about the migrating from an app using MVC, Spring MVC to Web Flux. So yeah, Reactor is the, so to speak, the plumbing for Web Flux. But you can also return reactive types, RxJava2 or Reactor from an MVC controller. And as Jürgen was saying earlier, this will, like Spring Framework will do its best to deal with that, and it will basically adapt to servlets async mode in the background. But you cannot, to best of my knowledge, you cannot mix an MVC endpoint and a Web Flux endpoint. Like it's still MVC in the background that deals with it. But it can help with your migration because you start familiarizing with Flux and Mono and all these APIs that will gradually seep into your service layer and stuff like that. And then when you make the move to Web Flux, it will be easier. But you cannot really mix and match, so it has to be progressive. My advice would be also to start exploring, like choose a boundary, probably your service layer, where you start to put some reactive code in there. And that also will make the migration easier. What else? With MVC, I don't think you could use reactive. I might be wrong, actually. I don't think you could use Spring Data, reactive Spring Data, but I might be wrong. Yeah. But yeah, so you have to take like baby steps, so to speak. Yep. Yeah.
You were talking in the end about things like automatic buffering that will happen to control backflow, and I'm assuming that you can also configure what would happen, for example, if your queue fills up, if it's just gonna drop things or do something else. Is that something you would typically need to configure in a real-life application if you're working with Reactor, or can I just rely on the defaults for, let's say, my 90% use cases?
So, how do you choose, like, do you deal with back pressure, and how do you choose to deal with back pressure? So yeah, first, indeed you can choose to do stuff like dropping. If the source, let's say your source publisher, original publisher is an array of sensors, temperature sensors or something like that, and it gives very frequent signals, and your use case is just a dashboard where you update it every second and you don't care about every single value, you can say, okay, if the source still emits a lot of values that I'm not interested in, you can like drop the elements on a time window, for instance. So you could do that. The other part of your question was, do you typically deal with it in like 80% use case application? And I'd say no. Most of the time, you don't have to resort to back pressure, changing like back pressure behavior operators. No. You might have to deal with back pressure, application level back pressure on your subscriber side. Like use that to instruct the whole chain that you are ready to consume about that much data. That you could do. And otherwise, the default is just telling the publisher, send me as much data as possible, like as fast as you can. I don't care. I'm ready for it. So, yeah, I think most of the time you would either do that, like how do you say, unbounded request, or do a particular request of n elements. But most of the time, I don't think you usually use the on back pressure drop kind of operators. But they are there. Yep.
You mentioned that we have this queue created to handle back pressure.
Mm-hmm.
Is the queue created even in case of cold publishers? Because there you typically don't deal with back pressure issues, right?
So, yeah, I think most of the time it is created. And it's used like as an intermediate buffer. So there would be cases where it's not actually needed, it's drained right away. But sometimes when you don't request maximum amount of elements, you need to store a few intermediate elements, like if there is a race between two steps, or if data comes in very quickly, you have to have that small buffer to still honor back pressure and not miss any element. That's the essential part. The queues are there to ensure that everything works fine when there is to avoid race conditions, basically, and dropped like unseen events. So they are always created. And that's also why we create this kind of optimizations, because in Reactor you have a Flux and Mono. Mono is a subtype, specialized type of Flux. It's 0 or 1 element. And for that use case, if you use a lot of monos in your application and say you do a lot of flat maps to combine them in your application, it has an overhead. And this optimization helps with that and helps having a performance that is close to imperative code.
Yep.
Yeah.
I have one more, if
Yep.
I may. You mentioned about this work stealing.
Yep.
And how it happens. But can you give some more examples on where it's used internally and what it is about? Because
typically, Flatmap will use that sort of pattern. So if you have a few elements that comes into a flat map, for each element you decide to process them in asynchronous manner. So you do another asynchronous call, which returns a flux or a mono for each of these source values. And Flatmap will flatten that into a single stream of results. And sometimes, since it's asynchronous, two results could come in at the same time. And they could come in from two threads, basically. And they have to be emitted in the single thread in sequence, like a whole sequence that's not missing any step. And that's where work stealing would happen. There's only one of the threads that publish the data into the flat map that will win and do the work, actually. Yeah. Yeah.
Hey, I have one question about this API where I saw publish on and subscribe on.
Mm-hmm.
And it seems like, for me, like micromanagement, where you, as a programmer, have to optimize the treats. Can't we let the framework to decide how many treats we use, so we can maximize CPU utilization? And also related to that is this microfusion. I see that it tries to combine operations so that they can be executed in one treat. But isn't it contrary to the idea that we can split the work to different treats as much as possible to, again, utilize CPU better? Thank you.
So yeah, how does that play into maximizing CPU utilization? First, since everything is non-blocking, yeah, that will help tremendously with CPU utilization. The other part of your question was that you have to micromanage the threads. How do you do parallelization, basically, right? There's an operator for that. So basically, if you want to parallelize, you will use the parallel operator, which gives you a kind of slightly different flux. And the work of the parallel operator is actually, it's kind of weird at first, but first it divides the work into rails. So it kind of creates sort of several flux that correspond to like 1/3 of the data if you have said parallel 3, for instance. And then you will decide with which scheduler to run each of these rails. So you can say, okay, divide the workload equally between 5 rails, and maybe run these rails on that thread pool. So it's, how do you say, we split the concern of dividing the workload, the source workload, and where to run each of these sub-workloads. But that's basically parallelization, in a bit like in Java 8 parallel. It's 2 operators instead of 1. But again, you have, you choose when you want to parallelize, and otherwise, in most cases, it just works and it will run. Maybe it will run on a single thread, but it will run at maximum efficiency. And that's how, in Web Flux, you can serve a large number of requests using only 4 threads. That's how Web Flux works. Like, you don't have like 10,000 threads. You don't need that sort of limits. You have 4 threads, the native threads, and you serve like 100K requests on that. So it's really maximizing utilization this way. So yeah, just to say, most of the time you don't have to worry about that. If you really want parallel work, you have 2 choices. Flatmap is if it's more like I/O bound, and parallel if it's CPU bound. Does that answer your question? Yeah. Yeah. Oh right. Oh right. Yeah. So you have different architectures, and you would like the framework to choose for you. So first, Reactor is not a framework; it's a library. But still, if you use the default parallel scheduler, it's instantiated, it's created with the platform's number of threads of CPUs. I mean, so it will do that. Until recently, it would work less out of the box with stuff like containers, but the Java has changed and accounts for that now. So by default, if you have 8 CPUs, it will have 8 threads in the pool. If you have 64, it will have 64 CPU threads in the pool. It's kind of like that already. And if you find out that 64 is way too much, then you can initialize with a maximum or something like that. All right, I think we are out of time. Thanks again, and yeah, thank you.